this session in which we will solve some problems pertaining to entropy by means of the aid of a computer. So, in this problem we have 1 kg of ammonia contained in a spring loaded piston cylinder arrangement as a saturated liquid at 20 degrees Celsius. So, the state 1 is x equal to 0 and T equal to minus 20 degrees Celsius. Heat is added from a reservoir at 100 degrees Celsius until the final condition 800 kilopascal and 70 degrees Celsius is reached. So, the question is find the work done, heat transfer and entropy generation assuming that the process is internally reversible. So, for this particular process going from 1 to 2 there is no entropy generation. The meaning of internally reversible is this. So, how would the process look like? It is a spring mass, it is a spring loaded piston cylinder. So, what do you think the process looks like? The process is a straight line in the PV diagram. Okay. So, given this linear characteristics, it is a linear curve. Okay. So, going from one state to other state, the work done is rather easy. It is simply the area under the trapezium. So, work done during 1 to 2 is half P1 plus P2 times the total volume minus the initial volume, which is also half mass times P1 plus P2 times the specific volume difference. Alright, so let us first quickly get that out of the way. So, x1 is 0 and T1 is equal to minus 20 and P1 is equal to pressure of ammonia, T equal to T1, x equal to x1. And similarly, P2 is 800, T2 is 70 and V2 is volume ammonia, T equal to T2 and P equal to P2. We also have V1 is equal to volume ammonia, T equal to T1 and x equal to x1, and the mass is given as 1. So, the work done is simply the mass times half times P1 plus P2 multiplied by V2 minus V1. So, let us see what that comes out to be. So, the work done is 97.73 kilojoule. Okay. Let me just fix this window. Okay, there we are. So, the next question is what is the heat transfer? And so, to find out the heat transfer, we invoke the first law of thermodynamics, in which we have the heat transfer to the system is equal to the change in the internal energy. So, here we assume that the kinetic energy and potential energy difference in the internal energy are negligible, plus the work done by the system. Okay. So, here work is done by the system and there is a change in internal energy. So, let us find out what the heat transfer is. So, where now we have to define what the U's are. So, U1 equal to so there we go, and similarly U2 equal to okay. So, the amount of heat transfer to the system is 1447 kilojoule. Okay. So, now we recall that this is the heat transfer to the system. Okay. So, the entropy generation is now a contribution from the system and this particular heat transfer. So, for the system delta Sgen. I will not repeat the derivation of this because this is obtained by assuming that this is a single control mass. So, this is equal to delta S of the system plus delta S of the surrounding. Delta of the system is equal to mass times S2 minus S1 because of the very simple fact that entropy is a state function, and for the surroundings. So, if the system receives an amount of heat Q12, the surrounding has lost an amount of heat minus Q12. So, this will be minus Q12 divided by the temperature of the surroundings, which is 100 degrees Celsius, but that has to be converted to Kelvin. So, this will become 373.1. Okay. So, then let us write down minus Q12 divided by has to be converted to Kelvin. Okay. So, let us see what the Sgen is. So, we have obviously forgotten to define the entropy. So, we use the independent quantities T and X to find out the entropy at the first point. After that, we can use the entropy by we can find out the entropy by using the internal the independent properties temperature and pressure. I mean, you can also use internal energy, it does not make a difference. Basically, I could have used U equal to U2 over here, and it hardly makes a difference. Alternately, I could have also used V equal to V2. You need two independent properties to find out the entropy. Okay, so let us see. Okay, so Sgen is 1.307 kilojoule per Kelvin. Okay. In fact, let us see what happens if the work done, I mean somehow the spring does not do that much amount of work. Does it create more entropy? Does it lead to less entropy? What happens? So, let us say it is simply P1 times delta V, yeah, just hypothetics. So, the Sgen has increased slightly. Okay. So, if the process were to go on, I mean it will not go on, but I leave it as a small task to you. So, if this spring were not there, do find out what the final state will be, okay, the pressure will be constant, and then find out the change in entropy and see whether it is larger or smaller than 1.307, and then try to draw some, try to assess what is going on. Okay. So, with this we finish this particular problem. It was a rather straightforward problem in which we recall some of our old concepts, where the linear spring leads to a process which is a straight line in the PV diagram. Here we do not need to really evaluate the slope because both the points are known, and you simply join it by a straight line. Once the work is known, the heat transfer was determined using the first law, and then the second law was invoked to find out the entropy generated. We have made use of the concept that to find out the Sgen for the whole process, you can consider the whole system plus surrounding to be the control mass. In that case, the delta S is also the entropy generation, and that is found out using whatever is shown on the screen over here. So, with this we conclude this particular session, and I will be back next time with another problem. Thank you.